For every step, I'm multiplying by the same number, right? If I apply this formula k times, I'm multiplying the number k times, yes? This entire parenthesis is less than 1, or rather, actually, the magnitude of this expression has to be less than 1, right? I mean, I can't have minus 1,000. If it's minus 1,000, it's less than 1, but it doesn't work. So it's not it's the magnitude of this number is less than 1, and by magnitude I don't just mean the absolute value in the sense of real numbers. I mean the absolute value in the sense of complex numbers, right? So the condition for stability is the magnitude of 1 plus lambda delta t is less than 1. Okay, now if we look at this plot again, real of lambda and imaginary of lambda, I mean, how can we draw a region in this plot? Actually, let me duplicate the plot over here. How can we draw a region in the complex plane of real lambda and imaginary lambda for which the stability criterion for forward Euler is satisfied? Can you translate this equation into geometry? Think of the boundary, right? For what values of lambda would the absolute value be actually equal to 1? Unit circle? It's not going to be unit circle, right? Well, yes. It's actually the boundary equal to 0. It's actually a unit circle for 1 plus lambda delta t. You're right. You're right. So how do we shift the unit circle for 1 plus lambda delta t into a geometry, into a shape, just for lambda? First, let's get rid of this 1 plus, right? If 1 plus lambda delta t is a unit circle, how about let's subtract both sides by 1, right? So lambda delta t would be within a region that is the unit circle subtracted by 1. What is a unit circle subtracted by 1? You are shifting the origin towards the left, right? So instead of the origin of the circle being at 0, you have the origin of the circle somewhere on negative, actually at -1. So that would be, I mean, if I draw a stability region, if I draw a region for lambda delta t, it would be actually unit circle shifted towards the left by 1. So I would have -1 here, and I would be still a unit circle of unit radius. But that's for lambda times delta t. How about for lambda? Yeah, we then have to divide both sides by delta t, right? What is a circle divided? What is a shape over here divided by delta t? You're actually expanding starting from the origin, right? The origin doesn't change. Everything expands by a factor of delta t. So instead of the circle being at -1, the circle is now at -1 over delta t. And the radius, instead of being 1, the radius is going to be 1 over delta t. So this would be 1 minus 1 over delta t, and here would be -2 over delta t. So that would be the stability region for forward Euler. Okay. How well does that approximate the stability region of the real differential equation of the analytical solution? Well, it's hard to say, right? It depends on delta t. If delta t is very, very tiny, right? If delta t is very, very tiny, this point is very, very far away in the negative. And if you are looking into this region, I mean, it looks pretty much like the stability region of the real differential equation, right? But if delta t is not so tiny, then it doesn't really look like that at all. Actually, if I have a very negative lambda, right? If I have a lambda that is larger, that is more negative than 2 over delta t, the real differential equation would be stable and my forward Euler would not be stable. That's actually a huge problem. Not in this case when we are solving a scalar ODE, but when we are going to be solving a coupled system of ODE. It could be the case when an eigenvalue in the coupled system of ODE can be very, very negative and causing forward Euler to have problems. We're going to see that pretty soon.